Hey there, focus learners, and welcome back to The Explainer. I'm just incredibly excited to have you here today. Our mission right now is actually pretty simple. We're going to peel back the curtain on medical AI. We hear so much hype about artificial intelligence just totally revolutionizing healthcare. But today, we're skipping all the buzzwords. We're looking straight at its true engine, which is clinical data. It's messy, it's super complicated, and honestly, without it, AI literally doesn't exist. So let's jump right in. Now, I kind of want to hook you right out of the gate with a provocative question. Is an AI just a really, really smart calculator? Interestingly enough, from a regulatory standpoint, authorities often treat AI exactly like a medical calculator. Just a tool you punch some numbers into to get a result. But the reality of how these systems actually learn and process information, it's entirely different. They don't just compute, they actually uncover patterns. Okay, so let's quickly map out our journey for today's explainer. We're going to start with the Medical AI Foundation, then walk through the AI lifecycle, figure out how to make sense of health data, tackle the whole bias and data quality issue, and finally, look at why we absolutely need local data. All right, starting us off with Section 1, the Medical AI Foundation, and this massive shift in how we actually program things. So historically, in traditional programming, it was like a basic math problem. We gave the computer an input and a rule to get an output. Like, say the input is a patient's temp of 102 degrees Fahrenheit. The rule, which a human programmer wrote, is if the temp is over 100 degrees, the patient has a fever. And boom, the output is positive fever. It's very straightforward, right? But AI completely flips this equation on its head. We give the AI the input and the output, and we force the computer to figure out the rule itself. We feed it literally millions of temperature readings right alongside labels of whether those patients were actually diagnosed with fevers, and the AI goes ahead and creates the logic. That's the fundamental difference here, and it perfectly explains why data is the absolute bedrock of modern AI. Moving right along to Section 2, the AI lifecycle, or the practical mechanics of how this stuff gets built. So now that we've got a handle on the abstract coding concepts, we've got to look at how these tools are actually built for real, everyday clinics. Because building medical AI is a very linear, highly structured progression. Step 1 is identifying a specific clinical need, and this is crucial. You should never, ever use AI just for the sake of using AI. If a task doesn't explicitly benefit from it, don't build it. Step 2 is defining your target state. Step 3 is actually implementing it into the workflow, and Step 4 is relentlessly monitoring its performance. Let me give you a really clear example of what this looks like in the real world. Imagine a super busy radiology department. The explicit need here is that generating a chest x-ray report is just taking way too long. So, what's the target state? Well, it isn't some vague, fluffy promise of better accuracy. It's highly measurable. We want to reduce report generation from 1 hour down to 30 minutes. Once implemented, if the AI only brings the time down to, say, 45 minutes, the developers know they've got to update their models. Or if the time actually shoots up to 2 hours because the AI is super clunky to use, they literally just de-implement it right then and there. Everything is driven by a strict, measurable target. Which brings us to Section 3, health data types, and how we actually make sense of all this chaos. So where does all this messy data actually come from? Well, first up, we have the EMR, the electronic medical record. Think of this as heavily controlled data from just a single department, like cardiology. Next, you've got the EHR, the electronic health record, which essentially scoops up and aggregates all those separate departments across an entire hospital system. And finally, you have the total Wild West, the PHR, or personal health record. This is the patient-generated data, like the continuous glucose monitor right there on your smartwatch. It is incredibly valuable, but it's also completely unregulated compared to strict hospital data. Now, you might be wondering, why do we even want to pull from all those different sources? It's because of this concept right here, continuum data. Historically, healthcare data has been very episodic. You get sick, you go to the doctor, data is created, you go home, the data stops. But AI thrives on a continuous conveyor belt of information. To truly predict long-term medical complications, an AI model needs the entire continuum of a patient's life, from childhood immunizations in the EHR all the way to daily smartwatch biometrics in the PHR. A single snapshot just isn't going to cut it for a really good predictive model. But, well, here is the massive roadblock. Information that you and I understand easily is actually incredibly hard for machines to grasp. Right now, a staggering 75% of all medical AI development happens in just one area, radiology. Why? Because medical imaging is structured data. It comes perfectly packaged with strict metadata, neat little rows and columns that computers absolutely love. Meanwhile, a doctor's free-form clinical notes, those are semi-structured. They're full of weird shorthand and shifting contexts. And things like a patient's random Google searches are entirely unstructured. Trying to process that unstructured data requires a monumental effort before an AI can even begin to make sense of it. All right, let's hit section 4, bias and data quality, diving into the real dangers of messy data. So you've probably heard the old computer science phrase, garbage in, garbage out, right? But in healthcare, we have a much more dangerous twist on that. Garbage in, gospel out. Basically, if your data quality is poor, the AI's prediction is definitely going to be flawed. But the incredible danger in medicine is that a tired, overworked doctor might see that flawed AI output and blindly accept it as absolute, unquestionable truth. And to put that into perspective, when we're dealing with massive, raw, uncurated medical data sets, a massive 20 to 30% error rate is actually incredibly common. We're talking missing fields, random typos, entirely wrong contexts. If human experts aren't rigorously curating and double-checking this data before it ever reaches the AI, we are essentially building the entire future of our medicine on a foundation of massive errors. So, how exactly does this bias sneak in? Well, it happens in surprisingly practical ways. Just imagine an AI trained to detect pneumonia, but it was only fed X-rays from patients over the age of 75. Obviously, that AI is going to fail pretty hard at accurately diagnosing a 20-year-old. Sometimes this data variation happens during the cleaning process, where specific demographics are just inadvertently erased. And honestly, this next part is wild. The quote-unquote ground truth isn't always even true. In one study, 3 separate top-tier human experts were asked to annotate a single lung nodule, and they marked 3 completely different spots. I mean, if the human experts can't even agree, how on earth is an AI supposed to learn the correct rule? Which perfectly tees up section 5, the need for local data. Because context absolutely matters. Because of all those biases and variations we just talked about, medical AI models are shockingly fragile. You might have this brilliant, highly accurate AI developed at some world-class hospital. But if you take that exact same off-the-shelf model and plug it into a completely different local clinic across the country, developers routinely see a massive 20 to 30% drop in accuracy. The clinical protocols change, the patient demographics change, and the AI just instantly stumbles. Let me give you a really stark, unforgettable example to anchor why local data is just a non-negotiable. Imagine an AI designed to analyze a patient's cough. If you train that AI exclusively on patients in Singapore, where the air quality index is a nice, clean 75, it learns a very specific set of rules. But if you take that model over to New Delhi, on a day where the air quality index is a highly polluted 500, that Singapore-trained AI will literally fail entirely. The environmental context is just completely different. An AI simply cannot be globally accurate without that crucial local contextual data. And guys, this is exactly why human experts are totally irreplaceable. I know it's super tempting to just use advanced large language models to quickly organize messy health records, but the data shows that off-the-shelf LLMs can hallucinate, meaning they literally just make things up, around 15 to 20% of the time when extracting medical data. Even with intense fine-tuning, that error rate never quite drops to 0. A human domain expert absolutely 100% must remain in the loop to review the outputs, understand that vital local context, and catch these dangerous hallucinations. So all of this leaves us with our ultimate North Star question. Can AI truly help us provide the right intervention to the right patient at exactly the right time? As we've seen today, the math is definitely there, but the messy, biased reality of human health stands right in the way. So what do you think? Will algorithms eventually outgrow the need for our human intuition? Or will the human in the loop always be the absolute most critical piece of medical AI? Keep questioning the data, keep learning, and I'll catch you on the next explainer.